Okay, ME 4260, 5260 class. I hope you've enjoyed this little reading quiz on your pumping. I trust it wasn't too bad. Okay, so we're going to delve back into pumping and try to push through. Need to get through the pumping so we can get to the compressed air. We will go over that steam test one of these days. I just want to keep moving in this today, but we will go over it. That's a promise. Okay, this is the last slide I think that we did last time. And just a quick review. What we're looking at here is we have our three system curves right over in here, where I've got the red one is all frictional. This one, what is that, dark blue? I'm a little colorblind, but at any rate, so we have significant, we got about 100 feet of static head, and then we're frictional from there. And then this one, this kind of light colored blue-green one, aqua maybe, looks like that's 130 feet of static, and just a little bit of frictional head as we increase flow. So these are all drawn through the same operating point. I think this is what, 130, something like that. 130, 140, 141. I can't remember the number. Feet ahead. It's a little short of 150 and 4,500 GPM. And so three different types of systems. And we're going to see how this works with parallel pumping. And let's see, is this the... Let's see, now I take it back. This is the curve that we had last time. So we have our same three system curves, and this particular style of pump curve. So this is one pump, two pumps, and three pumps. And we talked through this, showing that for all frictional, as we turn on the second pump, we go, well, one pump is here, two pumps would be here, and three pumps is there. There's really no point in running three pumps on this particular all frictional curve because you just don't get anything back for running the third pump. The second pump, you get a little bit more, but still not very much. And then, of course, if we compare that to this almost all static head dominated system, one pump we're here, two pumps we jump way out here, and three pumps we even get, you know, a fair amount of additional flow out here. So this just shows how parallel pumping works better with static dominated systems than it does with friction dominated systems. And then the point of this slide is to just do it for a different pump curve. And we see that this pump curve, things work better, certainly for the static dominated system, at least. And also the friction, the all frictional system. So on the all frictional system, we're here. Second pump, we go on here. I don't know, what is that? Maybe 1,000 something GPM, not a whole lot. And then the third pump, we would go up here, which is only several hundred, 300-400 more than we are here. So this system, while better than this particular pump curve, still is not very good in terms of all frictional system curves. The static dominated curve, again, is pretty good. One pump, two pump, it doesn't quite double, but you get, we get what, 4,500 here, that's probably 3,000, 3,500, and then we jump out to here with three. So it works fairly well, significantly better. When you run an additional pump, you get a significant increase in the amount of flow. Okay. Okay, let's talk a little bit about flow control valves. Shifting the discussion a little bit. This is a typical curve for a particular valve. I don't think it says on here what the valve is, but you can get these from the valve manufacturers. And so this CV is the valve coefficient, the valve flow coefficient, the C sub V. And it gets used in a fairly simple equation like this. GPM, Q, the flow rate, is the CV times the square root of the pressure drop across the valve divided by the specific gravity. And so based on valve position, you can get this curve at any particular, you can read the position of the valve by looking at the handle, or there's usually a position indicator on the valve. Well, you can estimate it pretty close. Say if it was 50%, then you can read over here, it looks like this is about, the CV would be 120, between 120, 125. And so if you knew the flow rate, then you could use this equation to calculate the delta P for the flow. And notice the units on this, these do come with units. This is typical in the US. The delta P is in PSI. D stands for differential. And of course, I think we've talked about specific gravity. That's the density of your fluid that you're pumping or is going across the valve, divided by the density of standard water. Okay, and so if you just look at this, that requires that the units on CV be GPM divided by PSI differential to the 1/2. And of course, specific gravity is dimensionless. Now, there is also a geometry factor that can be included with this. And we'll talk more about this. If the geometry factor is 1, that would indicate that the upstream pipe, the valve itself, and the downstream pipe are all the same diameter, okay? And if not, then there is a geometry factor, I think it's an F sub P, that we can calculate to put in here. If you download the PSAT program, I'm hoping that it's still available. It comes with a valve tool, which is very, very handy. And I'll show some screens and probably demo that some today. If not today, then in the next class. But so, you know, when you're working with pinch valves, going to the manufacturer, getting the actual valve model number, going to the manufacturer and getting the appropriate curve of CV versus position is very, very helpful and a very common practice. You will also notice that at 100% open, this valve has a characteristic of, I'd say 540, CV of 540. And so that tells you and allows you to calculate a projected pressure drop when the valve is wide open. The fact that the valve is installed at all, even if you're not trying to pinch the flow, there'll still be some pressure loss just due to the fact that the flow has to go through the valve in its wide open position. Here's some more. These are for, I believe these are butterfly valves. And you see you have to get the curve for not only the model number, but the size of valve that you have. So these show 3 different, an 8-inch, 12, and 16-inch diameter CV valve. And so you can see just the variation as we start to pinch that handle down or pinch the valve shut. It's certainly not really very linear over the entire flow range. That's why you need to get the curve. Okay, so I've got some slides here that introduce PSAT, and we've already demoed it. I think we will just run through these quickly. The measure tool does the same thing, pretty much. It's just strung out, and we will get to measure here either today or in the near future, because it's probably going to be the tool going forward. But again, I can't emphasize too much. If you can still download the PSAT tool, I would definitely recommend that you do it. It's worth having. Okay, so the goal of PSAT, or measure, or measure, as the guys at Oak Ridge like to say, I don't know, is to assist pump users in identifying pumping systems that are the most likely candidates for energy and cost savings. And to operate it, you really, to do it right, you have to get out there in the field, get a little bit dirty, take some measurements, and figure out what's really going on. We like to measure things like flow rate, pressure, suction discharge pressures, motor power or current. Rotational speed is not on the list, but it's nice to have. And the programs use motor and pump performance data from the Hydraulic Institute standard, ANSI Hydraulic Institute 1.3, and Motor Master, which is a DOE software that has motor performance characteristics punched into it, or curve fit into it, to estimate existing and achievable performance, as we've seen. So, you know, that's the screen, and we punched around on this the other day, so I'll probably hit this fairly quick. But, you know, we've got two different conditions, A and B, just two separate analysis. It can be whatever, I mean, it's up to the engineer, the guy running the thing, whatever he wants these to be. They could be two separate pumps. They could be different operating scenarios for the same pump. You know, it's up to the guy that's putting the numbers in. We have the pump fluid information, motor, the operating fraction, how many hours does it operate a year, the cost of electricity, and then this is your field data, a flow rate, a head, either power or motor current, and a voltage. And then we get results over here. So we've got some more slides that break this down. So this is how the slides break it down. So inputs, condition A, B, results over on the top right, and then documentation. We'll go through this. And then in PSAT, you have access to background information, the motor performance stuff, and some other things by clicking that button. We'll see more on that. This is what comes up in PSAT. Information on pre-screening, some of which we talked through at the start of these pumping slides. Just some general information, but the pump efficiency curves, achievable efficiencies as a function of specific speed, and then the motor performance curves, which is probably the most used of this. And there also is a unit conversion program you can call it through this. The motor performance curves, I think we already demoed this, but you can get hard data on at the 25, 50, 75, 100% of motor load on percent full load amps, power factor, and efficiency. And then on the PSAT version of this, you have to just kind of interpolate in between. On the measure program that has motor performance built into it, you can actually select any load point you want, and it'll give you a readout of the exact numbers that it's seeing. So that's a little bit of a benefit that Measure has over PSAT. Then the pump head calculator. This is the up here. This is what you click on the PSAT screen. You go back. It's right here, and it takes you. And we demoed this last time, I think. And there's two configurations of it. One, this is the one that shows the suction tank with the elevation on the suction side of the pump, loss coefficients for any fittings or anything that's in here. You got an entrance loss for sure. That's a square edged entrance going into the pump. And then some discharge loss coefficients. We can have an overpressure, or it can be zero, atmospheric, elevation. Discharge gauge, you almost always have a discharge gauge, flow meter, and elevation of the flow meter off of your datum. And so this is just putting numbers in, and it calculates a pump head for you. This is the other geometry. You got a little pull down here. If you know the suction gauge pressure and elevation, you're not coming out of a tank, say, or if you just have a suction gauge, you can go to this geometry, and it does basically the same thing. This is the system curve calculator. There is one of these in Measure as well. Let's see, where do we? Let me go back. Here, it's right here. That's a pull down, and it'll ask you, do you want to fit a system curve for condition A, condition B, or both? Doesn't really matter. You know, it will potentially, if you tell it to, it will feed numbers back in for a head, or you can just look at what head, you use the equation, get a head, and punch it in there. Either way. And so, you know, we put a specific gravity because it calculates, someplace in here, it calculates pumping power. Yeah, the fluid power in horsepower. So it needs a specific gravity for that power calculation. The exponent that you want on your equation, it's a little hard to see there. And then you put in 2 points that are on the system curve, and bingo, it spits out the static portion of the head right here, and then the loss coefficient, which goes just a constant that goes there. The flow raised to whatever power you put in, and that's your system curve. The mathematics is very simple, but it's handy to have a calculator to do that for you. You can log analysis and then save them away, retrieve them, delete them, whatever you want. And so this is the create a new log file. Say you go into a new company, or it could be a new system, however you want to save this away, create a new log file, give it a name, and then you can add, you can save your whatever analysis you have to that log file. It'll save it. And then if you come back later and do another analysis, you can click add to existing log file, or you can retrieve from a log file, or you can delete an entry. So it's pretty easy. And you can tell it where to put them and all that. It's got a default directory, which is handy, but you can put them wherever you want to. So that's pretty simple. Okay, here is valve tool. We'll go through these, and then I'll probably fire it up and do a demo on it. But when you download the program, this is the folder. It's PSAT 2008. That's the last time it was updated. And then if you want to fire up PSAT, you just select this. If you want to fire up the valve tool, you select this. And so we're going to do valve tool, so we select this. This is not the screen yet, but we'll see the actual valve tool screen here in a second. This is some fundamentals. So the valve tool uses this equation, this valve equation, and notice here the F sub P is included, and the F sub P is programmed into the valve tool. So it's a very handy way to include any changes in diameter into the analysis. It automatically occurs when you put the inputs into the program. CV, valve flow coefficient, pressure drop, we've got an upstream and a downstream pressure, and specific gravity. So pretty straightforward. Nice little tool. Okay, so there's the what the valve tool looks like. We can set units, whatever system of, it's got 3 or 4 different system of units you can operate in. And then we basically have 4 inputs. We have flow rate, 2 pressures, and a CV. If you look back in this equation, you know, what do we have? You know, this is just a geometry factor, so it's a direct calculate. So you know, it doesn't count as one of the variables. So you got Q, CV, P1, and P2. That's all you got. So this is a pull down, and it says it gives you 4 options. So you can calculate CV from your flow rate and pressures, if that's what you know, or you can calculate your flow rate from your CV and your pressures, or you can calculate your upstream pressure from the other 3, or you can calculate your downstream pressure from the other 3. You got to have 3 of the 4, or be willing to guess. Okay, so you set this pull-down menu on, you know, whichever version, whatever you want to consider the unknown and the knowns. Put in your specific gravity. And in this case, we're going to calculate the CV, so we have to put in a flow rate. So the flow rate is 5,000. We put in an upstream pressure. We put in a downstream pressure. We put in our pipe diameter. So I've got 16 inch here, 16 here. And it's very common for a valve to be sized a little smaller than the piping. It gives it what they call more authority, more bite. When that valve starts closing, it has more impact on the flow. If the valve is too big, you might have to close it 50% before it really affects the flow. So if you downsize the valve a little bit, you have a larger pressure drop when it's open, but when you start closing the valve, it actually does something, you know, but 90%, 80%, you actually get a change in flow. If the valve is size the same as the pipe, you may have to close it to 70 or 60% before you do anything. And so you lose controllability. They call that authority in the control world, I believe. So this is a fairly common scenario. So we're showing a 12-inch valve and 16-inch pipe. We got 16 up and 16 down. We got our differential pressure. It looks like we're dropping 5 PSIG. It's possible that this pipe could be running up and down vertically, have a change in elevation. So the upstream gauge is 5 feet and the downstream gauge here is 2 feet. So that impacts the analysis. And then you get a calculated velocity. We're 8 feet per second. This is in the wide open. Yeah, is this wide open? Not sure that valve velocity, if that would, yeah, I think that would be at 12-inch diameter, I'm pretty sure. And then, so we're 8 because we're back to 16. And so anyway, and then we get a K value, the loss coefficient for the expander and the reducer, because we got to get from 16-inch to 12 and then from 12 back to 16. We get a K value for the valve itself. And we also get a K value total, which is just the sum of those. Okay. Up on the upper right-hand corner, this is, because it's going to do it's going to do cost calculation. So it's the same operating fraction. What portion of the year is a valve in this position? What's our cost of electricity? And what's your estimated pump and motor efficiencies? So in this case, we're 85 and 95. So it calculates the head loss in feet across this valve, the frictional power loss in horsepower, and that's what? Flow times feet of head times specific gravity divided by 3960. Simple calculation. What's the frictional electrical power when you take into consideration the efficiency of the pump and the motor? So how much pump energy are we really eating up with this valve in this position? And what is the annual cost? So say that the cost, if that valve sits that place for a year and you continue to put 5,000 GPM, under these operating conditions, it's going to cost you $7,433 in pumping energy. And say if that sits that way all the time, we could open up that valve and trim an impeller, put on a VFD. We have other ways to reduce the flow that don't waste the energy. So here's some examples. This is 12-inch pipe, 8-inch valve, measured flow rate 2,700, upstream pressure 85, downstream 72. We got pretty standard water at 70 degrees Fahrenheit, 5-cent power, and it operates all the time. So we want to find the valve flow coefficient, the loss factor K, the power loss, and the annual energy cost. So there you go. We punch it in, and so again, we're calculating CV from flow rate and pressure, so we put our information in. There's a note here, pump and motor efficiencies are often not known and must be assumed. Using high efficiency yields conservatively low power and cost estimates. You'd probably rather estimate it low than estimate it really high and be wrong. The calculated loss K values apply to the upstream pipe diameter, 12 inches in this case, not the valve size. So here's another example. We had 10-inch pipe, 6-inch valve. We got our pressures, water, all this operates continuously. The valve position is indicated at 60% open. Valve generic flow coefficient curve is available. So we have a curve. So estimate the flow rate, power loss, and annual energy cost. Well, so this is what happens. You go out in the field and you find a valve and you go, this is 60%, 40% shut, 60% open. So bingo, you go find yourself a curve for the valve. You go in at 60% and you read up and over. And so what is that for? There's 500, I don't know, 430, 440. You got to read the curve, read it at 430, and then you can put in, you have the pressures, you have the CV, so now we're going to calculate flow rate from delta P and CV. And so this produces a flow rate of, 1726, I believe that is. We've estimated our pump and motor efficiencies, electrical cost, all this. And so we're saying that the frictional loss is 18 horsepower, 16.7 kW, $73.35 per year being dropped across that. So it's nothing you can't do by hand, but it's a pretty handy calculator type tool. It's out there. Okay, we'll do this one then. Well, I'll go actually pull it up here. So this equation, this Q is CV times the square root of delta P over specific gravity, is only good for a while. If we look at flow rate and the square root of pressure drop, basically this is linear up into the point that we start get cavitation, which means that the pressure gets so low that we start forming vapor bubbles inside, on the exit side, inside the valve and on the exit of the valve. And if that gets too bad, we get what we call choke flow, which means that it doesn't matter what the stem position is, we can't get any more flow out of it. So this is called choke flow. So this is an ideal condition, and it happens for a while, but it doesn't happen forever. And so that's something that, if you're doing something that's pretty critical, you would want to check with the valve manufacturer and find out exactly for his valve, exactly where this flashing, this choke flow effect starts to affect the flow rate. versus the pressure relationship. Okay, so let me see, I fired this thing up, so let's do that. So if I come down here to my PSAT folder or someplace, PSAT right here, and there's valve tool, fire that guy up, and there you go. Looks just like the screen captures. So again, like I said, these are all of the different units. Yeah, like wastewater stuff, they pump a lot of water. It's like MGD, millions of gallons per day. Feet, inches, and PSIG. You can go metric, liters per second, meters, millimeters, kPa, or you can do larger flows, meters cubed per hour, etc. So you get to pick your units. And this is the pull down where you select, you know, which 3 pieces of information do you know? Are you going to have to guess and iterate around or something if you don't know 3 of them? But basically, we're assuming that you would know 3, and you know, whatever you can calculate downstream pressure. So here's a calculated downstream pressure from the other input. So anyway, that's I think, pretty straightforward. Those inputs, and then you just put in this information, and you can log, so you can create a log file, then you can retrieve previously logged information. So that's pretty handy. So I think we'll get rid of that. All right. Okay, so let's look into more depth and detail about developing these system performance curves. But first things first, develop a simplified flow diagram. Capture critical elements of the system. How do you do that? Review the P&ID drawings and piping diagrams that may be available. Talk to operators. And that's always nice to walk down a system because they always forget to tell you that they've changed a bunch of stuff from the diagrams that they give you. And so anyway, just to get more information about the system. Okay, so here's a simple system curve. So you see the form, head total head required at a given flow rate is a static head plus this K prime, and this is a loss coefficient. This is unique to the system curve. I mean, we use K's all over the place, so this isn't the previous K that we had for like a valve loss coefficient, K times V squared over 2G. It's not that K. This is K prime. It's a different K. Just like H gets used all over the place, enthalpy and convection coefficient and all that. So I don't know why, but we have certain variables that we just use all the time. Q is flow rate, typically gallons per minute. C is just the exponent that we want to assume, usually 1.9 or 2. And then the frictional head or dynamic head is that product, K prime, Q, the flow raised to the C power. And so when you look at that, it's like H's total head is equal to static head plus the friction head. So you're just going to add them together. So the static head, that's caused by overpressures in tanks and elevation differences. So it has nothing to do with flow rate. And the frictional head has everything to do with flow rate. It basically varies with the square, almost the square of the flow rate, whatever exponent you want to use. Okay, so here's an example. What do we got? We got a couple tanks. We got one right behind us, which is fairly small, fairly low. And then we're going to pump up on the hill. We have the potential. to have gas overpressure, P1 in the suction tank, and P2 or P4, which would be in the discharge tank. And so we'll throw some numbers in this. We're also showing suction in a discharge gauge on the pump and a flow meter. And for this little example, we assume that we have the same size pipe. Because, if we have different size pipe, then we got a change in velocity head from suction to discharge. And so at least right here, we're going to just assume we got the same pipe on both sides. Okay. So sources of static head, elevation, and
I think we can hear you now, Doctor.
can you hear me now?
Yes, we can hear you now, or at least I can.
Well, if you can, I guess the rest can. Okay, thank you.
You're welcome.
If you can't, let me know. Let's see. So we should still be recording. Yep, we're still recording. Okay. I haven't had any trouble with the mic up until now, but hey. Okay. So elevation, we can measure it, we can estimate it, whatever, we'll see. Okay, here's one way. Sometimes your suction tank may be down in the basement and you're pumping up 6 floors or 2 floors or whatever. Well, you can actually count the number of steps. Somehow you got to find a way to estimate. So we're saying what? We say 32 steps times 7.5 inches a step is 240 inches, which is 20 feet. Plus we've got 8 feet. So you want the elevation from free surface to free surface in the tanks. And so on that second floor, we've got 8 feet of fluid in the tank from the floor. And then, of course, in the basement, we have to subtract off that 5 feet to get the elevation from free surface to free surface. So anyway, that's just a little example. You could go back to high school geometry and try to do triangulation if you wanted to. Whatever is valid. You could count rungs on the cooling tower ladder and take a tape measure and measure one of them and then multiply it out. Okay, so here's a little equation. So we're assuming that we would measure these pressures in PSIG, which is pretty common in the US. And so that delta P, P4 minus P1 times 2.31, the 2.31 will convert standard water to feet of head from PSIG. And then if your specific gravity is not 1, you can still use the 2.31, but you divide by specific gravity. And that will produce the feet of head, of static head. Now, if those tanks are both open to atmosphere, then P1 and P4 are the same, and so that drops out. But you could have one tank could have pressure on it, the other tank not. I mean, it depends. Some people put nitrogen blankets on tanks. We see that pretty commonly. Keep oxygen away from whatever the fluid is. could be reactive or cause a problem. Keep water vapor away from a fluid. That could cause a problem. And then just the elevation, the Z4 minus Z1. So there you go. So in this example, we've got 20 PSIG at P4 maintained. We got 10 at P1. So we subtract and we got 10 PSI. G is the difference times 2.31, 23.1. Elevation difference of 40 feet. So my total static head is 63.1 feet for this particular system. Now it's possible to put the suction tank up on a hill and have the discharge tank down in the valley. So then that elevation difference could be negative. So the static head can be negative, 0, or positive, just depending on how this works out for you. Okay, or here's a trick. You can use the pump head calculator in PSAT to calculate your static pump head. So if you look at it, he puts in the same pipe diameter. He puts in 0 flow, so it doesn't really matter, but he's going to, so we stick in the same diameter. And so we just put in the downstream pressure gauge at the tank was 20, the upstream was 10, and we put in, then for the elevation head, we put in 0 here because the discharge elevation is 40 feet ahead of it. And we put in 0 for, because this is all frictional stuff, specific gravity of 1, and bingo, look at that, 63.1. So if you're creative, you can use the pump head calculator to do your static. But it's so easy to do, I don't even usually do that, but you know, it's possible. Okay, let's see. So for a second system head capacity point, we can always use the pump head. So basically we need 2 points. And usually we try to take the 0 flow and the static head because that's usually really easy to do. So, but we have to have a second point. And if the pump is operating and you can walk up to it, a lot of times the simplest approach, measure the pump head at the operating flow rate and let PSAT do the rest of the work for you. Why does this work on a system curve? Because the pump head and the system head at the operating point are by definition equal, because you know the pump curve and the system curve cross at the operating point. So you know that wherever that pump is operating has to be on the system curve. Okay, measured data. So you can go up to the pump, and you know if you can take these measurements. Say we use our strap-on ultrasonic flow meter, or maybe the plant has a flow meter. So by hook or crook, we come up with a flow we have some confidence in at 3,000 GPM. P2 is the suction pressure, and it's in a 16-inch line. And P3, and you see the pressures there, it's in a 14-inch line, schedule 30 stainless. The elevation difference between the gauges is 1 foot. And so I've got 53 on the discharge and 12.6 on the suction. So bingo, put that in the PSAT pump head calculator, and I get 94.7 feet. So, and notice when Don did this, he didn't just, he went and found the actual, for this pipe, which is what, schedule 30 stainless, he went and found the real diameters. He didn't just put in 16 and 14. He went and found, based on that schedule pipe, with the actual diameters, and all that stuff's available to you. The rest of it, and you can see the calculation of the pump head. So the other, so we've got 94.7 feet at 3,000 GPM. That's our second point to fit the system curve. And so there you go. This is from PSAT. So specific gravity 1, loss exponent 1.9. We put in the 3,000 GPM at 94.7. And by the way, it calculates the fluid horsepower. And then the point 2 was the static head at 0 flow, 63.1 at 0 GPM. And if you can put in an alternate point in here and it just puts a dot. Like that might be a point you were interested in highlighting something, and you can do a screen capture on this or whatever you want to do. And so here's your curve. This is head total is 63.1 plus this coefficient, that's K prime, times Q to the 1.9 power. There you go. And you can actually export curve into an Excel sheet, and it will save a little Excel sheet and put that information in there. I usually just write it down on a piece of paper and punch it myself, but by hook or crook, it's easy to get that into Excel. If you click retain this, it will carry this back into condition A and populate the head and flow input data with this, or you can say ignore changes, go back to PSAT. You can put in the numbers however you want to. So, okay. Tell you what, let me jump out of this. And I've got an Excel sheet. Thought I'd show you some of this. This is some analysis. Maybe, if it comes up. The things that happen in here. There we go. Whew. Okay, so this is an example of doing some pumping analysis. I don't remember exactly what all this stuff is, but we'll figure it out. Make it big enough you can see it. Okay, so this is a condenser tower pump number 2 from someplace. So this was my pump curve. Okay, so I got a copy of this off a website, or the plant gave me a copy. This is 1750, a standard RPM, and this is just taking the pump curve, picking points from what the pump could do. So 0 GPM, 125 feet. It started out, it was just that first little bit was straight. So 200 GPM, 125, 400 GPM, 124.7, all the way down. Estimate it down. Okay. Then you can plot that. So this curve right here, well, look how nice and smooth. Did I do some smoothing on that or what? I guarantee you, when I first plotted that, see, there you go. I'm just plotting that curve. And I say, okay, that's my base pump curve. Okay, piece of cake. Get the pump curve, punch the number, smooth it out, make you a nice plot. Y'all can do that. Okay. Then I took my strobe out there in the field, and yeah, there's the 1750 curve. It's 1789 is what I measured. Well, that's a little faster. So let me take that into consideration. So that's the number I'm pulling. This is just a tag over the columns. And so see, in this curve, it's D9, which of course I start at 0, but anyway, and then I adjust it. I'm locking down F6, which is this, divided by D6, which is this. And so you see at this 200 GPM, when I translate that point, it translates into 204.5. And that's the speed ratio to the first power, okay? When I translate head, though, the head translates as the second power. So I take that same speed ratio and I square it, and then I multiply it by the 125 feet times this divided by this squared, and it translates the head to 130.6. And then, so that gets copied all the way down. So all of these, this is the speed ratio times whatever the flow is here. So 3170 at this higher speed will translate into 3240.6. And this 52.5 translates into 54.9. So I've translated all of these points over to operation at 1789. And then I plot that curve. So if I click on this one, it should show that that's being plotted. There it is, right there. Okay, so for my analysis, if that's what I measure, this is my adjusted pump curve based on my true operating speed. So that's the capabilities of that pump at that speed according to the manufacturer. Now, that's if the impeller's good, and that's if this representative curve was representative of my pump when it was operating at 1750. There's lots of possible variation of it. My impeller could have some chunks taken out of it, you know? I mean, how long has it been there? When was the last time you opened it up? What's it look like? I don't know, man, we never opened it, you know? So, whatever. Okay, so then this is the measured operating point. Now, I don't, most of the time it doesn't really fall on the where you want it to, but you know, anyway. And so, and then this is a system curve. So this was an all frictional system, didn't have static head. And so this is a measured flow rate and pump head. So, you know, it's easy. You go to PSAT, you do the math, and let's see. So let's see which curve is which. There you go. So this is the throttled system, because what these people were doing, they had a valve closed. Okay? So the design point on the system is out here. So if you open the valve all the way open, the design point was 3,000 GPM. But these guys were, what is that? That's about 15, what's that, 1,800. Looks like about 1,800 GPM and operating on this pump curve. Okay, well, so you put that in PSAT, and let's see, throttled system curve. So there is no static head, so it's just the flow coefficient times the flow raised to the 1.9 power. And bingo. So I take all of my flows. Doesn't matter which flow, which one. I'm using D9. Okay, I'm using these flows, but it doesn't matter. You could use these flows as well. And you run out your system curve, and then you plot it up. Okay, so my analysis tells me that's where these guys are operating. Okay, now, you know, how am I going to save them energy? Well, they're dropping a huge, look at the feet of head dropped across the valve. Those valves, I think this thing actually had two valves on them, and they were both pinched. Because they couldn't pinch it. If they tried to pinch it with one valve, they got cavitation and they tore the valve up. So they said, well, we'll pinch this one a bunch and we'll pinch this one a bunch to get the flow down to where we need it, because this pump is grossly oversized. What had happened is they took out a chiller. Instead of having two chillers, they had one chiller, and they were too cheap to do anything to the pumps, or just didn't. And so they said, well, and the chiller people come in and say, you're pushing way too much water through that condenser, you're going to wreck the condenser. So then the chiller people start throttling the valves to protect the condenser, but the pumping energy, you know, just becomes a huge waste. Okay, so the idea here is let's open the valves and come out and operate on this curve, and then let's slow this puppy down until we operate right here. And my goodness, this is far less energy. Look at the savings in head. You know, what is that? That's about 27, 28 feet. versus 120 feet. I mean, that's just outrageous. Well, so what you do is, you estimate this. Well, this is just one more system curve. You've got your design operating point, what the pump's supposed to be capable of. You've got your zero static head. So you just fit another system curve, which is this one, plot it up, goes through there. Then this is kind of a cool trick. So now you plot another curve, and remember, I'm 1080 on my speed. You don't know exactly. I guess you could try to do a calculation, but if you get this program, let's say you start guessing speeds. So if I put in 1500, whoops, well, where'd my curve go? Well, see, this is this pump curve, but I can adjust the speed at which it operates, and the curve jumps. So you say 1500 now, because I'm not going through my desired operating point. So you can say, well, 1400. Well, it's getting closer. $1,200. I'm getting there. So anyway, you play around with it. 1080. Oh, ta-da! Goes right through my operating point. And then I can go back to the pump curve and I can determine the pumping efficiencies and everything. Put that in PSAT. And PSAT will tell me. So I can put this initial point into PSAT. I've got 1800 GPM at 120 feet ahead. I can put in this 1800 at, say, 28 feet ahead, put in the appropriate pump efficiency. Well, what I have to do for pump efficiency, I have to guess power. I guess power until it displays the pump efficiency that I want. And then I look at the operating cost before and after. I got savings. So anyway, this is kind of how the game gets played. And well, let's see. Well, let's do this. We haven't fired up measure in here yet for pumping. It's got another new version. Every time you open it, they've corrected something or added something. I tried to download this a couple times last night, and sometimes their downloads bomb. I don't know why. So I'm not sure not gonna try it right now. So anyway, but I was playing this. This is a pumping assessment. So this is the pumping. So you got system set up. This is where you start. It's a similar format to the STEAM program. System set up, and then you do assessment settings. You go 1, 2, 3, 4. Then you do assessment. You got diagram report, and got some calculators here. So this is just setting your units. What system of units do you want to work in? And you can customize any of this. This is the imperial, which is what I usually stay with. And then there you go, pumping fluid. Well, golly, it looks an awful lot like PSAT, because that's what they've tried to do, is mimic PSAT. The part that I don't really like, that I like about PSAT, is you have it all on one screen. Well, you got stuff spread out on umpteen different screens, and you got to go find stuff. And, I mean, I tell you, PSAT is, as far as software, pretty close to perfection. Old Don Cassida that wrote that, he's about as good as it gets. These boys at Oak Ridge, they're pikers compared to Don. I'm telling you, he's first class. And I mean, he really, not only is he a great engineer, an intuitive engineer, but he was the real guy that went out and did the work. So he knew what was important. He knew what you wanted to see, and he knew what you could bury in the background and really not go looking for and not worry about it. These guys are smart people, but they're not really pumping experts. And so, they're doing the best they can. They're trying their best within their framework to recreate PSAT. And in some cases, they've made improvements, for sure. Some of the tools, some of the motor performance characteristics give you more capability and stuff. Okay, well, so fluid and pump, this is, I think, pretty much the same stuff, you know, and it's got some nice pictures that jump up and all that stuff, you know. But, you know, pictures really only go so far. I mean, you know, once you know what you're doing, you don't really need to see between the bearings impeller or overhung impeller. I mean, you know, it's nice, but it's kind of like, you know, when you've been driving a car for, you know, 15 years to tell you, you know, how to work an automatic transmission or something. Just I show you a picture of you know, drive, you know, low, the different shifts. I'm going, come on, man, I don't, you know. But anyway, I don't want to pound these guys too bad. They are friends of mine. So RPM, direct drive, or belt. Oh, now see this, we got different types of belts built in here. You got V belt, you got not synchronous, specified efficiency, and that's nice. So, you know, Don only had one, either had a belt or didn't have a belt. So that's an improvement, see? So we get some stuff. Water, look, we got all these fluids built in. So you can just specify a fluid and you get properties and you don't have to go look. So that's good. I'm gonna have to quit ragging on these guys, I guess. Temperature, specific gravity, say, and let's see. There you go. See, it adjusts specific gravity for you. Now, see that, you know, that's like one of my test questions. You know, I give you something and tell you to go calculate the specific gravity and see if you know what I'm talking about. Viscosity and all that. So you got that. There's your motor. 60 hertz, 50 hertz, that didn't change. Rated power, you just put it in. That's fine. RPM, different types, same stuff. Voltage, and then you can put in, let's see, full load amp. This is just motor. This isn't field data. So, and you can estimate your full load amps somehow. I guess that is the estimate of the full load amps. Okay, and then your field data. So this is what you measure out there. Electrical cost, same thing. Flow rate. Head, here's your head calculator. And guess what? It looks pretty much just like the other head calculator. Let's see, so, and then we can measure KW or we can measure current, just like before. Put in your measured power, put in your voltage, bingo. And it right there, it estimates, you got operating hours, 8760, and so it estimates the annual cost of operation there. And then we get into the assessment, and we're about out of time for today, so you can look at this. You can do the novice view or the expert view. So I don't know. It's just similar stuff. But anyway, we'll talk about this next time. We'll go on through this. Okay, so you guys have a great rest of the day, and I will see you on Thursday. Thanks very much.